There have been moments in human history when everything seems to function so smoothly that we forget a fundamental truth. The world we live in has never truly been stable. We grow accustomed to lights turning on every evening, to GPS signals guiding us with meter-level precision, to networks of satellites quietly circling Earth, like invisible gatekeepers of modern civilization. All of this repeats day after day, creating a feeling of near absolute safety, an illusion that everything is under control. Yet that stability, when viewed from a cosmic perspective, is no more than a thin mist resting on the surface of a deep lake. Calm above, but beneath it flow currents that humanity has never truly controlled. All it takes is a single flash from the sun, the star more than 150 million kilometers away, and that familiar order can be shaken. No collision is required, no asteroid, no apocalyptic scenario borrowed from science fiction films. A brief surge of energy on the surface of our parent star is enough to distort GPS signals relied upon by millions of vehicles. Satellites that appear motionless can tremble slightly within invisible waves of charged particles. And on the ground, power lines stretching thousands of kilometers may strain under abnormal induced currents, edging closer to overload. What is striking is how few of us recognize this fragility. Modern technology works too quietly. Backup systems conceal minor failures. And when nothing collapses before our eyes, it is easy to believe we have overcome the risks posed by nature. But that belief is not grounded in the universe's permanence. It rests on a brief span of time, during which nothing has yet been tested severely enough. The sun, the source of life on Earth, lies at the center of this illusion. Its warm morning light makes us forget that beneath its gentle appearance is a colossal energy machine, where superheated plasma flows churn endlessly, where magnetic fields stretch, twist, and release energy in ways far beyond human intuition. We view the sun as a symbol of stability, but to the universe itself, it is a dynamic entity, constantly in motion, constantly changing. And then, in recent days, newly released images from NASA have caused the scientific community to slow down, look more closely, and reconsider questions that once seemed settled. On the surface of the sun, an unusual bright region has appeared. It does not resemble the familiar features recorded in previous cycles. It is a sign of a high-energy plasma eruption, powerful enough to temporarily distort the surrounding magnetic structure. These images carry none of the drama of sensational headlines. There are no doomsday warnings, no countdown clocks, no firm predictions that disaster is imminent. Yet it is precisely the calm with which scientists regard this phenomenon that makes it more noteworthy. In space science, the quietest signals are often the ones that demand the closest attention. The data indicate that the sun is entering a phase of activity stronger than originally predicted for the current cycle. Plasma eruptions are not rare, but their frequency and intensity are increasing in ways that require constant adjustments to existing models. This is not a sign of abnormal rebellion, but the natural rhythm of a star approaching the peak of its 11-year activity cycle. The problem is not that the sun is doing something wrong. The problem is that humanity has built a world overly dependent on the relative stability delivered by the previous cycle. We have grown used to a well-behaved sun, accustomed to geomagnetic storms appearing only occasionally and at manageable levels. And so every sign of increasing activity becomes a quiet but unmistakable reminder. the calm we experience is not the universe's default state. NASA's images do not say that catastrophe is coming. They do not predict any definite near-future scenario. What they truly do is pull the curtain back slightly, just enough for us to see that behind the gentle light, there have always been immense forces operating according to their own laws. Laws that do not care about flight schedules, do not concern themselves with national power grids, and certainly do not adjust their rhythm to the conveniences of modern civilization. This, then, is not a story about fear, nor is it a warning meant to alarm. It is a reminder, subtle yet impossible to ignore, that the sun has never been a quiet source of energy. It has merely aligned for a brief moment in history with humanity's need for stability. And as unusual signs begin to appear, the important thing is not panic, but learning to face reality. The stability we trust may be nothing more than a pause between stronger pulses of the universe. To understand why the year 2025 draws so much attention, we must step back and view the sun not as an unchanging source of light, but as an entity with its own rhythm. For billions of years, the star at the center of the solar system has operated in regular cycles, rising and falling, quieting and erupting, like the breathing of a colossal organism. The most familiar of these to modern science is the roughly 11-year cycle, during which the sun's magnetic activity shifts from calm to maximum and then returns. During solar minimum, the sun's surface is relatively clean. Fewer sunspots, fewer eruptions, and a steady, gentle solar wind. But as the cycle moves toward maximum, that order begins to change. Sunspots appear more frequently, magnetic field lines twist more tightly, and energy accumulates in increasingly large active regions over time. This is not meaningless chaos, but the natural consequence of superheated plasma flows moving within the star. The current solar cycle, cycle 25, began around the end of 2019. When the first data were analyzed, most solar physicists believed it would be a relatively mild cycle, comparable to or even weaker than the previous one. Statistical models based on data from recent cycles suggested that the peak activity of cycle 25 would likely remain moderate. There were no clear signs that an intense cycle was ahead. Relatively gentle, comparable to or even weaker than the previous cycle. Statistical models based on data from the most recent cycles all suggested that the peak activity of solar cycle 25 would likely remain at a moderate level. There were no clear signs indicating that an intense period of eruptions lay ahead. But the sun, as usual, did not fully conform to those expectations. Only a few years after cycle 25 began, observatories started recording unusual signals. The number of sunspots rose faster than predicted. Some active regions appeared with unexpectedly large sizes, persisting across multiple solar rotations. M-class and X-class X-ray flares, the strongest categories recognized by science, occurred more frequently than originally anticipated. These figures were not enough to confirm an extreme scenario, but they were sufficient to force researchers to reassess their assumptions. The year 2025 is expected to mark the peak of solar cycle 25. In scientific terms, a peak does not refer to a single moment, but to an extended period during which the probability of strong events reaches its highest level. This is similar to Earth's hurricane season. We know storms will be more frequent, but we cannot say which one will become dangerous or where it will make landfall. What makes 2025 distinctive is not a prediction of catastrophe, but the convergence of two rare factors. First, the sun is entering a phase of stronger than expected activity. Second, for the first time in history, humanity possesses an observation network dense enough to track nearly every fluctuation of this star. Missions such as SDO, SOHO, and the Parker Solar Probe do more than capture images of the sun's surface. They directly measure the solar wind, magnetic structures, and plasma flow, speeds at distances never before explored. The data returned by the Parker Solar Probe have been particularly striking. The spacecraft has approached the sun more closely than any human-made object ever has, skimming the region where the solar wind is born. There, its instruments recorded higher than expected plasma velocities, sharply fluctuating particle densities, and magnetic fields that change in complex ways with each pass. These measurements suggest that processes are unfolding inside the sun that current models have yet to fully describe. Some scientists propose that the heightened activity of cycle 25 may be linked to variations within the tachocline, the transition zone between the sun's radiative core and its convective outer layer. This region is where much of the sun's magnetic field is generated and reorganized over time. If plasma flows, they oscillate according to secondary rhythms not yet fully understood. They could amplify surface activity during certain cycles. These hypotheses are still under investigation and serve as a reminder that human understanding of the sun remains incomplete. What must be emphasized, however, is this. Even if solar cycle 25 proves stronger than expected, it still falls within the range of behavior the sun has exhibited in the distant past. This star has undergone countless solar maxima long before humans existed. The difference today is that we live in a world deeply dependent on technology, systems that are highly sensitive to even small variations in the space environment around Earth. Thus, 2025 is not remarkable because it breaks natural laws, but because it more clearly exposes the interaction between two different rhythms, the ancient rhythm of the sun and the fragile rhythm of modern civilization. When these rhythms fall out of sync, effects that seem minor on cosmic timescales can become significant in human life. Solar cycle 25, with its peak around 2025, is therefore not a deterministic warning. It is more like a natural test, not of what the sun can do, but of how well humanity understands the star that sustains it, and how prepared we are for fluctuations that have always existed in the universe. When people think of solar storms, many imagine something violent and visually dramatic, fiery explosions tearing through space. In reality, the most significant aspects of these storms lie beyond the reach of human senses. They do not roar, emit sound, or announce their presence. Most of the time, they move through space in absolute silence. What makes them consequential is not their appearance, but the energy they carry and how they interact with the invisible forces surrounding Earth. From a distance, the sun's surface appears smooth and stable. Beneath that brilliant light, however, lies a turbulent ocean of plasma, where superheated matter flows constantly, colliding and twisting along complex magnetic pathways. Energy here is never at rest. It accumulates gradually like a tightly compressed spring, and when a temporary balance breaks, that energy seeks release. One form of release is the solar flare, bursts of radiation that occur almost instantaneously when magnetic field lines twist to their limits and snap, the stored energy is unleashed as X-rays and ultraviolet radiation, traveling at the speed of light. For Earth, the effects arrive with almost no delay. Within minutes of a powerful flare, the ionosphere can respond, altering radio wave reflection and causing temporary communication disruptions. Flares, however, are often only the opening act. The phenomenon with more lasting consequences is the coronal mass ejection, CME. If a flare is a flash of lightning, a CME is a massive wave. Billions of tons of plasma and magnetic field hurled outward from the sun. These clouds of matter are not always directed toward Earth. Most drift into deep space, leaving no trace in human affairs. Only when a CME is launched in the right direction does the story become significant. Over a journey lasting from tens of hours to several days, a CME travels through interplanetary space, carrying its own magnetic field. This field is the key factor determining its impact upon reaching Earth. Danger does not arise simply from size or speed, but from how the CME's magnetic orientation interacts with Earth's magnetic field. If the two align in a way that effectively unlocks the system, energy can pour into the magnetosphere far more rapidly and intensely. Earth's magnetic field acts as an invisible shield, deflecting most of the solar wind and protecting the atmosphere from being stripped away. Under normal conditions, this shield is strong enough to maintain stability. But when a CME with an opposing magnetic field strikes, the shield can be compressed, distorted, and set into oscillation. Like a metal shield struck by a heavy blow, it does not shatter, but it vibrates violently for a time. Those vibrations propagate downward into the ionosphere, the upper atmospheric layer where radio waves reflect and satellites operate. Particle densities change, navigation signals drift, communications become less stable, and systems dependent on precise timing can experience errors. All of this occurs without any visible physical damage. No explosions, no flames, only subtle changes in an invisible environment upon which modern civilization depends deeply. What makes solar storms so difficult to predict lies not only in the CME itself, but in the convergence of multiple factors. A small CME, if it carries the right magnetic structure, can still trigger a strong geomagnetic storm. Conversely, a massive CME with weak magnetic coupling may produce only mild effects. This subtlety prevents science from issuing absolute forecasts. Instead, it can speak only in probabilities and scenarios. From a broader perspective, solar storms reveal that the universe operates primarily through forces humans cannot directly sense. We do not feel magnetic fields. We cannot see plasma. We cannot hear the solar wind. Yet this silence does not mean harmlessness. It reflects the limits of human perception, not the true scale of influence exerted by these phenomena. During the peak year of a solar cycle, an increase in flares and CMEs means that the window of risk opens more often. Not every opening leads to a significant impact, but each one places modern civilization into a mild state of testing. Not to destroy it, but to remind us that even our most sophisticated systems depend on the delicate balance of invisible forces in space. The essence of solar storms, then, is not violence, but subtlety. They do not come to annihilate, but to reveal the deep connection between Earth and the star that has sustained it for billions of years. By understanding flares, CMEs, and the invisible forces they carry, humanity gains not only insight into an astronomical phenomenon, but a clearer sense of its place within a far larger system. one in which stability is never absolute, and everything moves according to laws beyond our everyday perception. If the sun is the source of these invisible storms, Earth is where their consequences gradually unfold. Between the two lies a protective layer that most people have never seen or felt, yet rely upon every day to survive: Earth's magnetic field. This invisible shield not only keeps compass needles pointing north, but acts as a vast barrier, silently deflecting most charged particles arriving from space. Under normal conditions, Earth's magnetic field operates steadily and draws little attention. The solar wind flows continuously, sliding past the magnetosphere and maintaining a dynamic balance that has existed for billions of years. But when a CME carrying large amounts of energy and a compatible magnetic structure approaches, that balance begins to be tested. The moment a CME reaches Earth does not resemble a physical collision. There are no brilliant flashes or thunderous explosions. Instead, what unfolds is a slow yet powerful process of compression. Earth's magnetic field is pushed back toward the planet, shrinking like a rubber ball squeezed by an invisible hand. Magnetic field lines vibrate, oscillate, and reorganize themselves to adapt to the new pressure. It is this chain of reactions that gives rise to what science calls a geomagnetic storm. A geomagnetic storm is not a single event, but a prolonged process that can last from several hours to several days. Its intensity is measured by indices such as Kp, ranging from 0 to 9, reflecting the degree of disturbance in Earth's magnetic field. At low levels, these fluctuations are nearly imperceptible in everyday life. But when the index rises, especially during strong storms, sensitive systems begin to respond. One of the first regions to be affected is the ionosphere, the upper layer of the atmosphere where solar radiation ionizes gas molecules. As the magnetic field is distorted, the ionosphere is repeatedly compressed and expanded, like lungs breathing rapidly. This disruption alters how radio waves reflect, making long-distance communication less stable. In some cases, GPS signals may drift, not because the system itself is malfunctioning, but because the medium through which the signals travel has changed. Higher above, satellites pass through regions of space directly influenced by geomagnetic storms. As streams of high-energy particles pour in, solar panels are exposed to elevated radiation levels, while delicate electronic components face an increased risk of interference. To prevent damage, many satellites are designed to automatically enter safe mode, temporarily shutting down non-essential systems. For people on the ground, these decisions often appear only as brief interruptions, sometimes unnoticed unless they coincide with particularly sensitive moments. The effects of geomagnetic storms do not remain confined to space. As Earth's magnetic field fluctuates, induced electric currents can form within the ground and propagate along long conductive structures such as power transmission lines. Under normal conditions, these currents are extremely weak, but during a strong storm, they can intensify enough to place abnormal stress on transformers. Systems designed for stable electrical flow must then operate defensively, coping with fluctuations they were never meant to endure. It is important to emphasize that geomagnetic storms do not heat the Earth, do not produce dangerous radiation for people on the ground, and do not directly threaten life. The planet's thick atmosphere and strong magnetic field continue to perform their protective roles effectively. What is primarily affected is the technological shell humanity has built around modern life. It is our deep dependence on these systems that makes magnetic disturbances noteworthy. From another perspective, geomagnetic storms also give rise to one of the most visually striking phenomena nature has to offer, the aurora. When charged particles penetrate the atmosphere near the polar regions, they excite oxygen and nitrogen atoms, producing flowing bands of green, purple, and red light across the night sky. During strong storms, the boundary of the auroral zone can shift to lower latitudes, creating rare displays in regions unaccustomed to such sights. That beauty, however vivid, is also a sign that Earth's invisible shield is being distorted under pressure from space. Geomagnetic storms, therefore, are not enemies of life, but part of the long-standing interaction between Earth and the Sun. They remind us that this planet does not drift through space in isolation, but exists within a continuous flow of energy from the solar system. When that flow intensifies during periods of solar maximum, Earth's natural shield vibrates, but it does not collapse. Understanding geomagnetic storms does not make humanity less dependent on technology, but it does sharpen our awareness of the limits of control. The systems we build, no matter how sophisticated, must still adapt to invisible forces that existed long before civilization emerged. And it is through that adaptation that humans learn to live more harmoniously with the greater rhythms of the universe. Amid all the silent and invisible effects of geomagnetic storms, there is one phenomenon rare and beautiful enough to make people stop and look skyward in pure wonder: the aurora. Throughout history, it has been seen as an omen, a sign of the divine, or the fire of ancient myths painted across the sky. Today, science has unraveled the mechanism behind auroras, yet their beauty still retains the power to make humanity feel small beneath the vastness of the cosmos. Auroras are not independent phenomena. They are the direct consequence of disturbances that begin at the sun, travel through space, and finally reach Earth's invisible protective layer. When a geomagnetic storm occurs, some charged particles manage to breach the magnetosphere and are guided toward the polar regions, where magnetic field lines converge. There, these particles plunge into the upper atmosphere at tremendous speeds, colliding with atoms and molecules of gas. These collisions do not destroy the atmosphere, they simply transfer energy. When oxygen and nitrogen absorb this energy, they enter an excited state. As they return to their original state, the excess energy is released as light. That light is the aurora, slow-moving, undulating curtains glowing green, purple, red, or blue, depending on the type of gas involved and the altitude of the interaction. Under normal conditions, auroras appear only at high latitudes near Earth's poles. This is why regions such as Northern Europe, Alaska, and Antarctica are among the few places where people can regularly witness them. But when geomagnetic storms grow stronger, these boundaries begin to shift. The luminous bands can spill into lower latitudes, appearing far beyond the aurora's usual domain, and lighting skies where most people never imagined such colors could exist. In those moments, the beauty of the aurora becomes more striking than ever. It is not merely a spectacular sight, but a signal that Earth's invisible shield is under significant stress. Each dancing ribbon of light is evidence that the magnetic field is oscillating, that solar energy is finding deeper pathways into the planet's protective system. That beauty, therefore, is inseparable from the turbulence that creates it. There is a fascinating paradox in how humans perceive auroras. To the observer, they are moments of stillness and poetry. The night sky seems to slow, and the gentle glow evokes a rare sense of calm. But on the physical level, auroras are born of violent motion, charged particles racing at high speeds, magnetic fields vibrating, and the atmosphere constantly adjusting to new energy flows. The serenity we feel is merely the perspective of a small creature standing beneath the sky, not the true state of the forces at work above. During the peak years of a solar cycle, the increased likelihood of strong geomagnetic storms also means that unusual auroral displays may occur more often. This is neither a promise nor a certainty, only a possibility that has occurred before and may recur when similar conditions align. For science, auroras are observational tools, helping researchers understand how solar energy is transferred to Earth. For humanity, they are a vivid reminder that this planet is not separate from the events unfolding in deep space. Crucially, no matter how brilliant they appear, auroras pose no threat to life on the ground. Their light does not carry dangerous radiation at levels that can directly harm humans. They merely mark disturbances in the upper atmosphere, where technological systems, rather than biological ones, are most affected. In this paradox, auroras become a perfect symbol of the relationship between beauty and risk in the universe. What captivates our eyes is also a sign of forces beyond our control. Perhaps that is why auroras always evoke a dual feeling. They are both a rare visual gift from the cosmos and a reminder that the stability we take for granted can be disrupted at any time. Standing beneath a glowing sky, humans are not only witnessing a natural phenomenon, but unknowingly observing a moment when Earth is interacting directly with its star. In the broader story of solar storms and geomagnetic disturbances, the aurora is like a climactic passage of music, not loud, not destructive, but powerful enough to illuminate the entire composition. It shows that chaos does not always wear a frightening face. Sometimes it arrives as soft light across the night sky, reminding us that even amid the universe's most intense upheavals, there exists a beauty that makes us pause, observe, and reflect. For most of human history, people lived beneath the sky, without imagining that the sun could ever be a disruptive force. It was a source of light, warmth, and order, a symbol of life itself. Even as astronomy advanced, the sun was still regarded as a stable machine, operating predictably according to familiar laws. That perception remained intact until one morning in September 1859, when it was shattered for the first time. On September 1st of that year, British astronomer Richard Carrington was observing the sun through a telescope at his home. His work was routine, sketching sunspots and recording how they changed over time. But midway through his observation, he witnessed something never seen before. On the sun's surface, near a large group of sunspots, two intensely bright regions suddenly flared into existence, erupting violently for several minutes before disappearing. Carrington initially suspected a malfunction in his equipment, but the phenomenon was real. That day, the sun had released one of the most powerful solar flares ever recorded in human history. What made the event extraordinary was not only the eruption itself, but what followed. Just 17 to 18 hours later, an exceptionally short time by interplanetary standards, Earth began to respond. This indicated that a CME of extraordinary speed had been launched directly toward our planet. When it struck the magnetosphere, Earth's invisible shield was violently distorted, triggering one of the strongest geomagnetic storms ever known. The consequences spread across the world, not by destroying life, but by shaking the foundations of 19th century technology. Telegraph systems, the backbone of communication at the time, began behaving erratically. Wires sparked, telegraph machines transmitted signals even after power sources were disconnected. Some operators received mild electric shocks when touching equipment. In several places, messages could still be sent, using only the induced currents generated by the geomagnetic storm, without batteries or external power. At the same time, auroras appeared at latitudes never before recorded. Night skies glowed across the Caribbean, Mexico, and even near the equator. Many people awoke believing dawn had arrived. Contemporary newspapers reported that the light was bright enough to read a book outdoors at midnight. For those without scientific understanding, the spectacle was both wondrous and terrifying. Crucially, in 1859, humanity was not deeply dependent on electrical technology. There were no national power grids, no satellites, no GPS, no internet. And yet, the geomagnetic storm was still powerful enough to expose the fragility of the earliest artificial systems humans had built. If the Carrington Event could cause such disruption in a world like that, the natural question follows: what would happen if a similar event occurred today? Before answering that, it is important to understand the historical significance of the Carrington Event. It was not merely a rare astronomical accident. It was the first time humanity had direct evidence of a causal link between solar activity and disturbances on Earth. Before 1859, auroras and magnetic disruptions had been observed sporadically, but never connected into a clear chain of cause and effect. After that year, science began to change its view of the sun. It was no longer seen as a passive energy source, but as a dynamic system capable of releasing energy on a scale that could affect the entire planet. The Carrington Event became a reference point, a worst-case scenario used by researchers to assess the risks of space weather. Notably, no storm of equal magnitude has been recorded since. But that does not mean it was unique. Geomagnetic studies and ice core data suggest that similar events may have occurred in the distant past, before humans had the tools to observe and document them. Carrington was simply the first moment when humanity was modern enough to realize it had been touched by a force from beyond Earth. A deeper level, the Carrington Event is not a story of catastrophe, but of awareness. It did not end civilization, erase cities, or render Earth uninhabitable. Instead, it left behind a profound question in the history of science. How much control does humanity truly have in its relationship with the star that sustains life? Carrington inadvertently witnessed the moment when the illusion of absolute stability was lifted. Since then, with every passing solar cycle, the memory of 1859 has quietly persisted in models, scenarios, and scientific debates. It stands as a reminder that, however rare, extreme events are a natural part of the solar system. And as humanity grows ever more dependent on increasingly intricate systems, the Carrington story is no longer just history. It becomes a hypothetical stress test for the present. A question without a complete answer, but one that grows more urgent as we move deeper into the age of globally connected technology. If an event comparable to the Carrington's storm were to occur in the modern world, it would not begin with panic. There would be no global sirens, no universal emergency alerts. It would begin quietly, as invisible forces always do. A powerful flare would erupt on the sun's surface, followed by a CME racing outward at unusual speed. And somewhere within space weather forecasting centers, scientists would realize, with growing concern, that its trajectory aligned alarmingly well with Earth's orbit. Unlike in 1859, humanity today observes the sun continuously. Dedicated satellites can detect eruptions within minutes of their occurrence. But observation does not equal control. Once a CME is launched, all humans can do is track it, model it, and estimate its arrival. The response window remains narrow, from several dozen hours to a few days, depending on the plasma's speed. During that time, the world continues to function. Aircraft still take off. Data still flows through fiber optic cables. Power grids still carry the enormous demands of billions of people. The fragility lies not in immediate collapse, but in the fact that modern civilization is built upon uninterrupted stability, in systems that are highly sensitive to magnetic disturbances. When the CME reaches Earth, a geomagnetic storm begins. The magnetic field is strongly compressed, and the first effects appear in the upper layers of technological infrastructure. Satellites in low and medium Earth orbit face sudden increases in radiation. Some automatically switch to safe mode, temporarily suspending data transmission. For users on the ground, this may appear as disruptions in navigation services, weather data, or telecommunications, systems long taken for granted. Global navigation systems are among the most vulnerable links. GPS does far more than guide individuals. It provides precise timing for financial transactions, synchronizes telecommunications networks, and supports critical infrastructure. When signals are disturbed or delayed, small errors can cascade into larger failures, especially in highly automated systems. On the ground, electrical grids become the most exposed point. Induced currents generated within the Earth can enter long transmission lines, placing abnormal stress on transformers. In worst-case scenarios, some equipment may suffer permanent damage, not from excessive demand, but from being forced to handle currents they were never designed to endure. Replacing large power transformers cannot be done quickly. Manufacturing and transport can take many months. What makes the modern scenario more complex than Carrington's era is not the intensity of the phenomenon, but the degree of interconnection. A failure in one region is no longer local. When power grids falter, supply chains are disrupted. When telecommunications degrade, coordination and response weaken. When navigation and timing systems fail, everything dependent on them is affected in turn. That said, it is important to emphasize a modern Carrington-level event does not imply the collapse of civilization. Disaster narratives often exaggerate destruction while underestimating adaptability. Today, many countries and organizations have incorporated space weather risks into operational planning. Some power grids can temporarily reduce load or disconnect during strong geomagnetic storms. Satellites are built with better shielding and more robust safe modes than those of earlier decades. Even so, a Carrington-scale event would still represent a systemic shock. Not a destructive one, but a revealing one, exposing how deeply humanity depends on invisible processes. For hours or days, the world might slow down. Some services would be interrupted. Some regions might experience prolonged outages. and within that temporary gap, humanity would be forced to recognize that modern convenience is not nature's default state. From another perspective, a modern Carrington scenario is also a test of preparedness and global cooperation. Solar storms respect no national borders. They affect the entire planet simultaneously in ways shaped by infrastructure rather than politics. This raises questions not only of technology, but of information sharing, coordinated response, and mutual support during rare but wide-reaching events. If 1859 was humanity's first warning, the 21st century is the first time humanity has the opportunity to act proactively. The difference lies in choice. We can treat Carrington as distant history, or we can see it as a mirror reflecting unresolved vulnerabilities in modern systems. In the silence of space, the sun continues its cycles, indifferent to the structures humanity has built. The question is not whether an event like Carrington can occur, but when it does, how well we understand it, and how prepared we are to adapt. More than a century after the Carrington event, humanity no longer stands before the sun in complete ignorance. We have built space telescopes, continuous monitoring satellites, and complex physical models to decode the behavior of the star that sustains life on Earth. Yet alongside this progress, a deeper question becomes increasingly clear. How much do we truly control, and where do the limits of prediction lie? Today, the sun is monitored almost without interruption. Space-based observatories continuously image its surface, measure magnetic fields, and track eruptions and mass ejections. When a powerful flare occurs, humans know within minutes. When a CME is launched, its trajectory and speed can be estimated within hours. Compared to the 19th century, this is an extraordinary leap forward. Yet space weather forecasting is not like terrestrial weather prediction. Earth's atmosphere follows patterns observed and measured over long periods, supported by vast datasets accumulated over generations. Solar phenomena, by contrast, occur in an extremely complex plasma environment, dominated by magnetic fields that change non-linearly. A small difference in magnetic structure can lead to a large difference in impact when a CME reaches Earth. The critical point is this: we may know a CME is coming, but it is very difficult to know exactly how it will interact with Earth. The orientation of the magnetic field within the CME, the key factor determining the severity of a geomagnetic storm, can only be confirmed when the plasma is already very close to the planet. This means that in many cases, humanity has only tens of minutes of precise warning before the strongest effects occur. This limitation is not due to lack of effort, but to the nature of the system itself. The sun is not a machine designed for human comprehension. It is a vast physical entity governed by laws science is still uncovering. Each solar cycle provides more data and raises new questions. Still, humanity does not stand idle before this uncertainty. Over recent decades, critical industries have begun shifting from passive prevention to active adaptation. Power grids in some countries are designed to monitor induced currents and reduce load during strong geomagnetic storms. Modern satellites include better shielding and operational safeguards to minimize damage during high radiation periods. Airlines track space weather to adjust polar flight routes when necessary. These measures are not meant to eliminate risk, but to reduce vulnerability. They represent a crucial change in perspective. Rather than believing nature can be fully controlled, humanity is beginning to accept that some forces can only be partially predicted, and that technology must remain flexible in the face of those forces. However, preparedness is uneven across the globe. Some regions possess modern infrastructure and rapid response capabilities, while others still rely on systems that are far more vulnerable. In a tightly interconnected world, these disparities create systemic weak points. Solar storms do not distinguish between rich and poor nations, but their consequences can propagate along existing fractures in socioeconomic structures. At a deeper level, preparing for solar storms is not merely a technical challenge. It is a matter of perception and expectation. Modern civilization has grown accustomed to the idea that everything is always available, always connected, always functioning. When a natural phenomenon disrupts that state, humanity's response is not only about fixing systems, but about confronting a sense of lost control. It is here that the limits of science become clear. Science can describe, forecast, and mitigate risk, but it cannot eliminate uncertainty entirely. And perhaps that is not a failure. It is a reminder that humanity, no matter how advanced, still lives within a system far larger than itself. If the Carrington Event was the first warning, then modern science represents the effort to transform that warning into understanding and preparation. But understanding does not guarantee absolute reassurance. It merely helps place risk in its proper context, neither exaggerating it into inevitable catastrophe nor dismissing it as insignificant. As the solar cycle continues to unfold, the question, how prepared are we, has no fixed answer. It shifts with each passing year, each new technology, and each lesson drawn from smaller events along the way. What matters is not achieving total control, but sustaining the capacity to learn and adapt. And perhaps it is precisely in acknowledging our limits that humanity moves closer to a more sustainable relationship with the universe it inhabits. Once all the facts are laid out, solar cycles, plasma storms, geomagnetic disturbances, the Carrington Event, and modern scenarios, what remains is not fear, but a deeper question. What kind of universe do we live in, and how do we choose to exist within it? The universe is not built to be stable in the way humans often expect. It does not promise continuity, nor does it guarantee that what holds true today will remain true tomorrow. The sun, long a symbol of life and order, is in reality a dynamic, ever-changing system, sometimes violent and utterly indifferent to the fragile structures humans construct around themselves. The stability we perceive is merely a relative pause within a long current of change. Throughout history, humanity has built civilization on the assumption that nature provides a fixed foundation. The sun will rise each morning. Earth will continue to turn. The laws of physics will not suddenly change. These assumptions are largely correct, but they conceal a subtler truth. Stability is not the natural default, but the result of continuous balance between opposing forces. Solar storms and geomagnetic disturbances do not disrupt the cosmic order. They are part of it. What is tested is not Earth itself, but how humans interpret their place within the system. When technology was simple, space-driven disturbances appeared only as strange lights in the sky. But as civilization has moved deeper into the age of electricity, digitization, and global connectivity, those invisible forces now touch the very structures we depend on. Here lies a central paradox of the modern era. The more humanity understands the universe, the more it realizes it cannot control it. Knowledge does not lead to absolute power, it leads to humility. Each advance in space weather forecasting does not erase uncertainty, it clarifies its shape. We understand risk better while also recognizing limits that cannot be crossed. The long-term lesson of the Carrington Event and of all future solar storms is not about preparing for an imagined apocalypse. It is about redefining safety. Safety is no longer the absence of risk, but the capacity to recover when risk materializes. A mature civilization is not one immune to disruption, but one capable of absorbing shock, adjusting, and continuing forward. This requires a profound shift in thinking. Instead of optimizing systems solely for maximum efficiency under ideal conditions, humanity must learn to design for non-ideal ones. Instead of assuming technology will always function seamlessly, we must accept the possibility of interruption and build layers of resilience, not only technical, but social and psychological. On a broader level, living in an unstable universe also means relinquishing the illusion of centrality. Earth is not the focal point of cosmic processes. Human civilization is not the sun's priority. We exist within a larger system where events occur not for humanity's sake, but regardless of it. This realization does not diminish human value. It places it in proper context. Value lies in our ability to understand, adapt, and cooperate, not in absolute control. Perhaps the most profound lesson solar storms offer is one about humanity's relationship with time. The solar cycle spans 11 years. Scientific history stretches only a few centuries. Modern electrical civilization is barely 100 years old. Set side by side, these timescales reveal the fragility of structures we consider permanent. Yet within that fragility lies a choice to deny it and live within an illusion of stability, or to accept it and build a more flexible civilization. Living in an unstable universe is not a curse, it is an invitation to see the world not as a pre-programmed machine, but as a dynamic ecosystem where everything interacts and evolves. In such a world, humanity's role is not that of a ruler, but of a conscious participant, aware that it is not outside nature, but within it. When the auroras fade and geomagnetic storms subside, Earth returns to familiar calm. Yet each time the universe leaves behind a reminder that today's peace is not guaranteed, that stability must be maintained rather than assumed, and that in the long relationship between humanity and the cosmos, wisdom lies not in avoiding all change, but in learning how to live with it. That may be the most fitting conclusion to this story. We do not live in a safe universe, but in a universe that can be understood. And the ability to understand, even imperfectly, may be the most durable foundation humanity has ever built. If you wish to continue exploring the scientific stories hidden behind the universe's apparent calm, from the sun and earth to human civilization, subscribe and follow the channel so you don't miss the next journeys of reflection.